Hi everyone, this is Sumit, and I'm going to summarize a paper called A Distributional Perspective on Reinforcement Learning. The authors of this paper are Mark Belmar, who is currently working with the Google Brain team at Montreal. He is also the author of the arcade learning environment that interfaces the Atari 2600 games and is used in several RL papers, including this one. Will Dabney is a research scientist at DeepMind London, and Remy Munoz is leading DeepMind's new office in Paris. In order to understand the motivation behind this paper, let's consider an example for which we would typically use RL to solve. Consider a commuter who wants to commute from station 1 to terminus. Most morning her train runs on time and she reaches her office relaxed and ready. But she knows once in a while an unexpected event can occur which would result in she being late for her office. The journey is composed of 3 segments of 5 minutes each, except that once a week the train breaks down, adding another 15 minutes to the trip. A simple calculation would tell us that if the train breaks down once every 5 days, it should take her 18 minutes on an average to reach her office. The Bellman's equation relates our current average prediction to the average prediction we make in the immediate future. What is a little counterintuitive about it is that we never actually observe these predicted averages. The train would either take 15 minutes or it would take 30 minutes, but it will never take 18 minutes. So when we model a value like 18 minutes, we are not modeling a part of reality. From a purely mathematical standpoint, this isn't a problem because decision theory tells us that we only need averages to make best choices. As a result, this issue has been mostly ignored in practice. The paper shows that there, in fact, is a variant of Bellman's equation which predicts all possible outcomes without averaging them. In this example, we maintain two predictions, a distribution, at each station. If the journey goes well, the times are 5 minutes, 10 minutes, and 15 minutes. And if the train breaks down, we have 20 minutes, 25 minutes, or 30 minutes. This means that the commute times are bimodal. These are the Bellman equations for the state value function and the action value function. What can we do with it? Well, let's say we can play this game to a superhuman level. So what is it that the authors are trying to do in this paper? They say let q pi be an expectation over a random variable. Here z pi is a value distribution. Then our Bellman's equation would look like this. The one take-home message from this talk is to remove the expectations. That is the simplest way to understand this paper. That brings us to the distributional Bellman equation. It says that the z pi is distributed like the distribution at the next state times the discount factor gamma plus the reward at the current state. There are 3 sources of intrinsic randomness here. One, reward R, transition p pi, and the value distribution at the next step. We would now define the distributional Bellman operator. An operator is a way of defining the expected behavior of your learning algorithm. So when you do reinforcement learning, you're going to sample states from the environment. You're going to wander around the world and try to learn about it. The one way to describe the average behavior is by looking at the operator. If I'm going to do one step of update, what would happen to my current prediction? This equation shows the Bellman operator for the expected case. For the distributional case, we have this equation, and these two equations are related to each other by this. Here, z hat pi is an approximation of the fixed point z pi, and t pi is the distributional Bellman operator. To give you a sense of what Does this equation really mean? We start with a prediction about the world Z. This prediction is a distribution at every state. We then apply p pi to it, and now p pi z denotes the next state distribution. Now we need to learn about this distribution. So we take this distribution and squash it with the discount factor gamma. Next we add the reward, and that is going to shift the distribution. This is just to give you a simpler picture. What happens in real uh, life involves convolutions and not just shifts and squashes. So if you have two possible rewards, you will convolve them with the reward function. So what we have in the bottom is the target that we would like to predict. When we talk about convergence of a reinforcement learning algorithm, we often talk about how it behaves when we repeatedly apply the operator that describes its expected behavior. The main idea here is that t pi, the Bellman operator, the regular one, is what's called a contraction. That means if we look at the distance between two value functions q1 and q2 and we apply t pi to both of them, they'll get closer together. Why this matters is because if we repeat this process infinitely many times, we'll get q pi, which is the fixed point or the target value that we are looking for. For the distributional RL framework, we cannot use this infinity norm. We need to find a probability distance in which the distributional Bellman operator is a contraction. The authors looked at KL divergence and found that if the support of the distributions are disjoint, the KL divergence is infinite. Hence, we cannot use this metric. They then looked at total variance and they found that if they took two distributions and multiplied it with the discount factor gamma, the distance between them was unchanged. So they couldn't use total variations either. That brings us to the Wasserstein metric, which is being used in this paper. In this graph, Fu and Fv are cumulative distribution functions of two random variables u and v. We define Wasserstein metric to be the probability mass being transferred from one CDF to another. In this simple example, it is the area between two curves. The formula for it is the integral between 0 to 1 of the inverse CDFs. The P norm generalizes this to give a family of distributions. There are three properties of the Wasserstein metric. The first one is that if we start with two random variables u and v and we multiply both these variables with a constant, the constant comes out. The second says that if we add another random variable a to both of them, their distance doesn't increase. The third one states that if we multiply these random variables with an operator a, the norm of the operator comes out. We now define the maximal Wasserstein metric as the supremum over states and action of all the possible Wasserstein distance between the value distributions z1 and z2. Next, we need to prove that this converges. Lemma 3 in the paper states that t pi, the distributional Bellman operator, converges to a unique fixed point z pi in dp bar for p between 1 to infinity. The proof is quite simple. You just need to use 2, 1, and 3. What we just saw is the policy evaluation setting, where we fix a policy and we look at the learning process, always applying Bellman update one step at a time. Another big setting in reinforcement learning is the control setting, where we want to learn about the optimal policy. So here, instead of choosing an action according to the policy pi, we are going to choose an action according to the max at the next step. So, what the authors try to do is apply some sort of operator corresponding to the greedy choice. That means choosing a policy such that we are greedy so that we maximize expected return. But unfortunately, they were not able to derive same kind of results that they have for the policy valuation setting. To prove this, they gave lemma 4 and proposition 1, 2, and 3. They collectively mean that the operator is not a contraction anymore. That basically means that as we try to learn the optimal value distribution, we are going to make choices based on the greedy policy, and that choice of the greedy policy is going to change based on our own guess. As a result of that, we converge to a policy that is non-stationary. That means this policy will change how it selects action based on time. In short, the distributional framework does not work for the control setting. That brings us to the algorithm that the paper presented. This is a deep queue network architecture that is designed to play Atari 2600 games. A DQN does reinforcement learning by having a deep neural network output the prediction of what the value of an action would be at a given state. So what the authors did is they replaced this value prediction with the whole value distribution. Specifically, it outputs discrete distribution with 51 possible values uniformly spaced on an interval. They call this algorithm C51, C for categorical, and 51 for the 51 value it predicts. The one key takeaway from this algorithm is that it's doing distribution to distribution updates. So what it really does is that it takes the whole distribution at the next state, it learns about it, and it backs it up to the current guess. They then applied this algorithm to the Atari suite of games and noticed that for a small number of predictions, this algorithm was performing very poorly. At 21 predictions, things got better, and at 51 predictions, it was better than the state of the art at that time. What we see here is the standard interface of ALE, the gameplay on the left hand side and the corresponding value distributions on the right. The x-axis denotes the returns and the y-axis shows the probability of getting these returns. The actions are coded with different colors. This is how the gameplay actually looks like. What the distributions really mean is better explained on my next slide. When the agent is unsure about whether or not it would get a reward, we witness a bimodality in the distribution. In traditional RL, we average these bimodalities out. This shows that value distributions are important as they help us learn richer models. The game on the left is called Sequest. Here the fish is quite near the ship. The agent can either turn and shoot the fish, getting a reward of 10, or the fish could attack the ship where the agent would receive a reward of 0 and die. The game of Pong on the right shows a similar dilemma as the agent isn't sure if the opponent would miss the ball or not. Whenever the agent is under pressure, we witness a good separation of the available actions. This is something very particular to value distribution. C51 quickly became the state of the art at the time of the paper was out. The graph shows its comparison with DQN, double DQN, dueling architecture, priority replay, and priority dueling architecture. Second graph shows percentage improvement over double DQN. This is another interesting result. This graph shows that not only is C51 better at playing these games, but it is also much faster to train than DQN. The x-axis is the training frames in millions. You can consider this as the time axis. and the y-axis shows the number of games that C51 won out of the total 60 games played. The graph shows that C51 got 75% of a trained DQN's performance in just 25% of the training time. On that note, I would like to end this summary and thank you for your patient listening.